So we have seen in module 1 as to what are the importance of satellite, okay, the textbooks that we're going to use, and where we're going to use satellite. Satellite is not only used for your television programs, entertainment, but it's also used for uh, military and the security purpose, right? The best advantage of a satellite is that it can broadcast to a larger area, and also um, it can reach the unreached area. Okay, for example, mountains, snow-capped mountains. Okay, and it's also used for remote sensing, right? So these were the things that we discussed in the previous lectures, and the frequency allocations, its uses, and how it's used in the Ku band, okay, from 12 to 18 gigahertz range. Of course, we use the other bands as well, L band and the VHF band. C band is also used, um, not as much as the Ku band, right? And then we saw few satellites as to when they were launched and its purpose, and how many countries are actually involved in deploying it, and what regions are covered. Okay, so yes, we talked about the Indian satellite system, INSAT, as well, the number of transponders, channels, and when it was launched, and the countries that it can cover, right? So these were some of the things. So for today's lecture, my idea is to talk about, your propagation impairments, which means something which drags down the performance of the satellite, parameters which can drag down the performance of a satellite. Okay. So the first thing that we all will have to understand here is the layers that the earth has. Okay, so as mentioned previously, our earth's atmosphere is made up of a lot of layers. Okay, so the first one that we can see is the earth's surface. Okay, this horizontal line that you can see, and then you can see the ice layer. Okay, so that is the layer, and we can see that from this point, so this is all in kilometers. Okay, so till up to about 90 kilometers, okay, we have a layer called troposphere, and then from 90 to 400 kilometers, this is where lots of communication happens. Okay, the ionosphere, because the clouds are charged electrically with the ions, and then from 600 kilometers onwards, it's all free space. Okay, where the environments are too harsh. Okay, so this is how we can actually look into the regions, okay, or the layers of our earth's atmosphere. Okay. So propagation impairments, so what are they, and what are some of the losses that happens? A signal traveling between an Earth station and a satellite must pass through Earth's atmosphere, including ionosphere, and this can introduce certain impairments. So a signal passing through from one layer to another layer is so difficult because it has to pass through the environment, it has to pass through uh, a lot of parameters, right? So a satellite launching itself is a big task, and maintaining the satellite and getting proper signals from it, okay, so that becomes a huge task. So some of the impairments that we see here is the losses due to atmosphere. So how are these atmospheres actually looking into the factors involved with respect to atmosphere? Atmospheric losses are the losses which occur in the Earth's atmosphere as a result of energy absorption by atmospheric gases. Now, this energy absorption actually is of great concern to us, because once the signal is absorbed, then how do we communicate, right? There's no point in communication, and it isn't called a communication. So, energy absorption by these atmospheric gases, is one such challenge, and these losses are treated different from adverse weather conditions. So along with this, we even have the bad weather. It could be rain. Many of you would have seen, during rain, sometimes that the television broadcast gets disrupted. Okay, so this is because of the attenuation due to rain. Okay, in simple, it's also called rain attenuation. Attenuation is something where the signal is getting degraded and there is a loss. Okay, so there are many things, actually to be considered when we look into satellite communications. Different types of atmospheric losses can perturb radio wave transmission in satellite systems. As we discussed, there are a lot of parameters which needs to be considered. Atmospheric absorption, this is one such important area, okay, where the energy is absorbed by the gases. And atmospheric attenuation, okay, weather related losses. Now some stats or some parameters that will have to be considered. Okay, atmospheric absorption loss varies with frequency or energy absorption by the gases, which varies with the frequency of radio waves. Now, as you all know, right, we mostly use the Ku band, which is about 12 to 18 gigahertz. And as our frequency changes, the level of absorption, the way how the environment reacts to the signal is different. Okay, right. So two absorptions are observed mainly, okay, at 22.3 gigahertz from absorption from the vapor molecules, okay, water vapor molecules, which is H2O. Now, as I told you, due to rain, there is a lot of absorption. Signal loss, 60 gigahertz from absorption in oxygen, just 60 gigahertz. Okay, just because of oxygen, there is so much of absorption that happens. Okay, frequency related. Now, if you can see this graph here, okay, I have plotted with respect to the total zenith attenuation, okay, versus frequency. So as your frequency increases, your attenuation also tends to increase, right? So you can see the previously discussed two parameters, which is H2O, which is because of water, two molecules of hydrogen and a molecule of oxygen combinedly called water, and just because of the O2, the O2 levels, right, the oxygen levels. So these are the 2 points that you can see exactly as we discussed at 22.3. You can see that the absorption is happening because of water, and at 60 gigahertz, it's because of the oxygen. So as your frequency increases, okay, the absorption and consequently the attenuation also increases. So you can see here towards your left hand side the losses, okay, that is happening, or the attenuation that is happening due to different parameters. The next thing that we can talk about here is the radio frequency waves which are attenuated in the ionosphere. Okay, remember I spoke to you about the ionosphere. So this ionosphere ranges from about 90 to 400 kilometers, right? And let us look into as to what can be their effects. Radio waves traveling between satellites and Earth stations must pass through ionosphere. There is no other escape. They have to pass through ionosphere. Okay. The ionosphere is the upper region of Earth's atmosphere, which has been ionized mainly by solar radiation. So the effect of solar radiation is high in ionosphere. These ionospheric disturbances, okay, now we all know how lightning occurs. We all know as to how, once the clouds collide, okay, due to the charges present in them, we can see lightning and ultimately thunder and rain, right? So this gives rise to fluctuations in the signal, and we will see what the effects are. Okay, so here you can see that the effects are actually mentioned, which is attenuation and sky noise increases. Then there is signal depolarization, refraction, atmospheric multipath, signal disturbances, reflection multipath blockage, okay, propagation delays, and intersystem interference. Now, these are some of the causes for signal degradation, and I've also written as to what can be the physical cause. Okay, for example, let's pick up signal depolarization. This can be due to rain and ice crystals. And what is the importance here? How does it impact? Dual polarization systems at C and Ku bands, okay, and it depends on system configuration. So the prime importance here is C and Ku bands. Now let's talk about the attenuation and sky noise. As the attenuation increases there, you can see frequencies above 10 gigahertz. So that's the region, where it's affected the most. Similarly, you can see your reflection multipath blockage, which is due to Earth's surface and objects, and the importance is mobile satellite services. So these are impacted, right? So you can just look into these details, right? So what are these ionospheric effects? Okay, you can see um, siltation. Okay, that is nothing but your ionospheric siltations are variations in the amplitude, phase, polarization, or angle of arrival of radio waves. The main effect of siltation is fading of signal. Okay, signal gets faded and ultimately gets degraded gradually. Okay, and the details are absorption, variation in direction of arrival, propagation delay, dispersion, frequency change, and polarization, rotation. So these are all the effects, and not only launching the satellite, we'll have to deal with all these effects one by one. Okay, which is actually a great challenge. So let us look into rain attenuation, and we'll try and understand as to what is happening here. Okay, rain attenuation is a function of rain rate. By rain rate is meant that the rate at which rain water would accumulate in rain gauge situated at the ground. The Met Department will actually look into all these details and inform, okay, as to how much of rain has occurred, and what are the levels or readings. Not only that, even at the base station, they will have all these facilities where they can look into the attenuation caused by rain. And rain rate is measured in millimeters per hour. How much of millimeters of rain has occurred per hour? Okay. Now this is a very important diagram, okay, which you will have to look into, which is about your path length through rain. So you have various parameters here, which is LG, HR, EL, elevation angle, slant angle, LS, the ice, okay, H naught, okay, then your LG. So we will see, and we will try and understand as to what these parameters are. In basic model, attenuation is in dB and is equal to specific attenuation, which is alpha, and this is the formula used. Rain attenuation A is equal to alpha L into dB. L, alpha into L dB, where L is the effective path length of the signal through the rain. LS, as I told you, it's the slant path. EL is the angle of elevation. HR is the rain height, which is the height at which freezing occurs. So there is a certain point, okay, there is a certain point here above which there is freezing of water, which is your water molecules H2O. Okay, it starts freezing and it starts getting converted into ice. So we will consider only this point, the point from where it starts raining and it doesn't freeze. Okay, the molecules, the water molecules do not freeze. So from that point to the ground level, that is your HR. Okay, so we will look into the details more, where your alpha here is into RP raised to B. Now this is also in dB per kilometer. Okay, so here you can see your A and B are dependent on the frequency and polarization. Okay, polarization and frequency are two such parameters in any communication that you can take, where you will have to polarize a signal, where you have to transmit a signal at a specific frequency, right? Electric field vector orientation related to the earth. So this is nothing but your polarization. And I have shown a table, okay, in which these values are picked up. For elevation angle less than or equal to 10 degrees, the determination of LS is complicated. If the elevation angle is greater than 10 degrees, then this is the formula that we are going to use, which is sine EL is equal to HR minus H naught divided by LS, where your LS is equal to HR rain height minus H naught and then sine the elevation angle. So what is this elevation angle? Let's get back to the figure. Okay, this is your LG, okay, which is at the ground level, the length of ground level, and your angle of elevation, this is horizontal, this is parallel, okay, to LG, and then the point at which we can actually get the rain molecules, okay, the water molecules, where it's not in the freezed format. So if we combine them, that becomes your angle of elevation. So these are specific values that you can use. These tables will also be given, okay, for your reference if required, or sometimes in the exam we will directly put this value so that you can substitute and compute the values that is asked for. Okay, so at 1 gigahertz, what is AH, what is AV, and what is BH, and what is BV? So these are the attenuation coefficients, okay, for the horizontal and vertical values, A and B values. Okay, so what is this A and B values? A and B depend on the frequency and polarization. A is here and B is here. Okay, so those values are picked up from this table. Okay, similarly, you can see that the Earth station, latitude and degrees, and towards your um, other scale we have rain height. Okay, so as the Earth station latitude degrees increases, okay, the rain height is actually reduced. Now how does it impact? It impacts a lot, because you can see here rain attenuation is dependent on HR, right, the rain height. So once the rain height changes, then your LS is changed, your slant angle is changed. Once your slant angle changes, your angle or your attenuation is also changed. Okay, so a lot of parameters we actually need to consider. Fine, so we will look into this details here, and we will try and understand as to how we have got these values. We will look into a few formulas, and probably with the numerical we will go ahead tomorrow. Okay, so today we will just look into the formulas, and I want you all to look into this and probably make a note of these formulas so that it can be used whenever we solve a problem. The effective path length, okay, L is equal to LS into RP. Okay, LS is your slant angle. Okay, and your RP, okay, RP is the reduction factor, which is a function percentage time P, and LG. LG we all know, LG is equal to LS cos EL. Okay, now LS is nothing but your slant angle, okay, and cos elevation angle EL. LG is your horizontal projection of LS. Now the information that we have here, okay, which is your your LG, okay, as I told you, the ground level. So LS is actually, if you draw a line, okay, here if you draw a line, a dotted line, okay, and if you make this line parallel to the earth's surface, that is when you will get your LG. Okay, so LG and LS should be the same. So keep that in mind. Okay. LG is the horizontal projection of LS. With all these equations together, the rain attenuation. So this is our final equation for rain attenuation. Okay, which is A RP raised to B LS into RP. So we will see, okay, what are these. As I told you, there are few standard reduction factors for 0.001 percentage. If P is equal to so much, then this is the formula that you will have to use. And if P is equal to 0. These are all your reduction factors. Okay, R is your reduction factor. And if P is equal to 0.01%, and what formula you're going to use here? Okay, 4 times of LG. So LG and these numerical values does change. When P is equal to 1%, then R1 is equal to 1. Now what are all these? Now if you can recall, right, this is your 1%, 0.1, 0.01, 0.001%, right? So as your earth station latitude increases and the rain height changes, it impacts. Okay, and this is how you get your percentages. Right. So the corresponding equations for circular polarization, okay, C represents circular, AC is your circular polarization, AH is your horizontal polarization, and AV is your vertical. So AH plus AV divided by 2 gives your circular polarization with respect to A, and with respect to B, BC, which is nothing but AH BH horizontal, vertical 2 times AC. So first you will have to calculate AC to get the value of BC. The attenuation for circular polarization is compared with that for linear polarization. So we actually do circular polarization as well as linear polarization. I have a problem here, so probably we will stop here and we will look into how to solve this problem, okay, based on the discussions we had so far. And please make a note of these formulas, okay, because we will be using them extensively. And you can actually draw the diagram and note down the formulas. The most important diagram here would be your rain attenuation, okay, the path length through the rain. Many times these questions can be asked for your exam point of view. Okay, so any questions, please feel free to post it, and we will always get back to those in the upcoming classes. Okay, thank you.